With the former video, we can now begin to start to understand what renormalization represents. Imagine we have two mirrors stationed in front of each other and they're fixed. They're not moving at all. They're motionless. And we have a real object in between, or a light source in between. That itself is motionless. In other words, the conditions existing from this point of the string to this point of the string across the open part of the string, as well as the information in the open part of the string, all three of those vectors are motionless. They're not moving at all relative to each other. However, once we start that process, first of all, if we understand that process, then we'll realize that a relative observer will not see the ball move, will not see the mirrors move, and because the mirrors and the ball is not moving, the reflected balls on the mirrors will not move. There's a state of no motion. However, what happens when we start to add variables here, start to put motion into the system, or movement, or direction? If we move the real object that is stationed between the mirrors, and remember now that because these mirrors are relative to each other, we don't just have two reflective points, two reflected bodies of information, but due to that entanglement we also now have infinite rows of recursion. At the initial state of the experiment, all points that are exactly reflected or recursively represented from the open part of the real ball. At this point of non-motion, no points in the system are moving. The whole system, infinite string, is motionless. However, if we take the real object that's stationed between the mirrors and we move it, change its direction, put it in a position, start to move it to the right, to the left, back, forth, up, down, spinning, revolution. If we start introducing that, then all points will begin to move. But all points will be more observed as moving in the recursion than the information that's on the surface of the screen. And that, again, drawing our attention back to the difference between the smooth and the perturbative component parts of this system as a whole, this whole string. So if we move the real object, then we notice that the recursive membranes renormalize. They shift, they change positions. And again, this is existing in the recursive interiors. If I move the real object toward the surface of plane A point string, then we'll see that the membranes start to move closer to the real object, or closer to the M field point of the string, beginning of the string. So this change at any given time, after moving it that way, the membranes move this way. If I move it this way, the membranes move back. Now if I start doing this, then you notice everything over here is reshifting. The recursive system over here is shifting with the movement. That means all points are moving relative to all other points. And here's where we're getting into renormalization. So I can renormalize the system in a myriad of ways, as I'm demonstrating. The potentials of how to move this system are probably, I would say, infinite, as far as if we got down to the microscopic fractions of moving from one degree to another degree, 360 degrees any which way. So I can renormalize the recursive aspects of the system in many ways. I can move the real object toward mirror 1 and thus away from mirror 2. If I do this, then all membranes, phase space, and the mirror dimensions as representing each slice are recursively represented, that are recursively represented in one side, will change position and change relative to each other. They'll do it in both sides. So all changes in matrix 1 will occur at the same rate and speed as the changes that occur in matrix 2, but they'll just be totally opposite. If this one's contracting at a certain rate, then this one will be expanding at that same rate. So these rates and speeds of changes to the interior are dictated by the rate and speed that the real object moves toward mirror 1 or away from mirror 2, or all kinds of variables of changes. This free-floating object in the interior, or the open part of the string, can move throughout that area. And as it's moving, all other points of itself, all symmetric copies of itself, are moving relative to that motion. So due to the entanglement of matrix 1 and matrix 2, we're also realizing that matrix 2 will change at the same rate as matrix 1, but really all the matrix, what's happening in the right matrix versus the left matrix, are actually opposite timelines facing each other. Okay, so though this is true as it regards renormalization, that the two sides move exactly opposite each other, it's not true of the speed of the change. And here's where we need to really zone in on a very important constant here. The speed of changes to all renormalizations occurring in both matrices, or both sides of the reflective recursive string, is entirely contingent upon the speed with which the real object moves toward or away from mirror 1 or 2. And the theory of relativity proves that if the real object is moving 10 miles an hour towards mirror 1, of necessity it's moving 10 miles an hour away from mirror 2. It also dictates that the mirrors themselves do not have to move. The dark matter planes that store the body of the black hole surface volume of information doesn't have to move. If the real object moves, then of necessity the mirrors are moving relative to it, even though that they're in a fixed position and aren't moving technically at all. So this means that all renormalizations are occurring at the same rate of change. Though the way they're changing is different in one side as opposed to the other, one contracting, the other expanding, one moving forward, the other moving backwards. All of those different changes, although it's totally opposite changes, the speed and the rates at which both sides are changing are consistent with each other, are exactly the same. So though the rates of change are consistent down the entangled string, the rates of change between membranes moving relative to each other one way or the other way, though it's consistent, and though the renormalizations are going two different directions, the speed of all changes in both matrices is the same. And that's the point I wanted to draw attention to. So what we're seeing in this model is that renormalization occurs because of the relativity of membrane to membrane and has separated by the phase space. So this phase space can either contract or expand. That is, the virtual distance between membranes can either contract or expand, or lengthen or shorten. If the phase space contracts, then the membranes are being pulled back toward the beginning, toward the event horizon, toward the surface. If the phase space expands, then it's pushing those membranes further from the surface and continuing the future expansion of the virtual part of the string. So this contraction and expansion, or shortening or lengthening of the distance between membranes, allows the membranes to move one way or the other. So I could renormalize either or matrix and cause them to change in whatever manner I wish by merely moving the real object in a variety of ways and rates of speeds. And when I say I can change the system recursively, I can say I can have complete control over the rate of expansion and contraction, the size on any particular membrane at any given time, the spin, the rotation, the speed, the vibration, the frequency, direction. Anything that happens is actually dictated by what's happening in the open part of the string and due to the relative motion, the motion of the real object relative to either or plane. I'll stop the video right here.